Okay, so we talked a little bit about interface last time, right? So we talked about the importance of having the interface of an object, of a base object, match the interface of derived objects. So now we're going to go into polymorphism, and this it's a long word for a very simple idea. Okay, so basically we're talking about if the interfaces are the same between the base and derived objects, right? So if we have the, for example, the shape object, or the shape class, the shape type, right? So if the shape type has a draw method and an erase method, then the circle, the triangle, the square, they basically change those same methods. Okay, so use the exact same interface between the derived and the base methods. Okay, and when possible, we don't want to add new methods to a derived object. We want to change the methods that are in the base object when possible. Okay, and this polymorphism idea is going to kind of illustrate why that is important from a design standpoint. Okay, and when I say it's important, basically in programming, things become important for a couple different reasons. One, you just want to write less code. The less code, the better. Okay, so whenever you can come up with a way to write less code to do more with less, it's always better. Because the fact that, less code is easier to maintain, it's easier to understand, shorter code is easier, it's just all, and that translates into cheaper to maintain, less costly to write, less stressful to maintain. Okay, it just is better. Okay, so less is better, all right, in programming. Okay, so when dealing with type hierarchies, you often want to treat an object not as the specific type that it is, but instead as its base type. This allows you to write code that doesn't depend on specific types. In the shape example, methods manipulate generic shapes without respect to whether they are circles, squares, triangles, or some shape that hasn't even been defined yet. All shapes can be drawn, erased, and moved, so these methods simply send a message to a shape object. They don't worry about how the object copes with the message. Such code is unaffected by the addition of new types, and adding new types is the most common way to extend object-oriented program to handle new situations. For example, you can derive a new subtype of a shape called pentagon without modifying the methods that deal only with generic shapes. This ability to easily extend a design by deriving new subtypes is one of the essential ways to encapsulate change. This greatly improves design while reducing the cost of software maintenance. There is a problem, however. With attempting to treat derived objects as their generic base types, circles as shapes, bicycles as vehicles, cormorants as birds, if a method is going to tell a generic shape to draw itself, or a generic vehicle to steer, or a generic bird to move, the compiler cannot know at compile time precisely what piece of code will be executed. That's the whole point. When the message is sent, the programmer doesn't want to know what piece of code will be executed. Okay. In this next section, they go through kind of Java's internal workings, right? Okay, they're talking about this bird controller object. We're going to go ahead and skip this for now. It basically talks about the internal workings of the Java language and how it's different from other programming languages. This for us, at our level, to be honest with you, you could go through a whole career without understanding this process, and you would probably be fine. Okay, and you might get into some situations where this would make a difference to you. For example, if you wanted to get stuff running as fast as possible, if you were working in an environment where you had to get the code running as absolutely as fast as possible. Okay. So anyway, so we're going to kind of skip this this binding, this how Java internally sets up this ability to use polymorphism. Okay, just know that Java can do it. All right. Okay, so we're going to get down to this example. Consider the shape example. The family of classes, all based on the same uniform interface, which was diagrammed earlier in this chapter. To demonstrate polymorphism, we want to write a single piece of code that ignores the specific details of type and talks only to the base class. the code is decoupled from type-specific information, and thus is simpler to write and easier to understand. Okay. And if a new type, a hexagon for example, is added through inheritance, the code you write will work just as well for the new type of shape as it did on the existing types. Thus the program is extensible. Okay, so we have a couple of words there, right? We've already learned a couple of words. All right. Okay, so decoupled here, we're just saying that that basically we're writing code that doesn't depend on derived versus base types, right? That the code is written for the base type, and we don't care about the derived types, as long as when we're adding derived types, we have the same interface, right? That we essentially use the same method calls. All right, and also it says the program is extensible. That just means that you can easily add things to the program. Okay, so extensible just means you can easily add on to the program without doing too much work. Okay. If you write a method in Java, as you will soon learn how to do, so we have void DoStuff shape s.erase, s.draw. Okay, so this is pretty easy to understand. So void is just saying it's a method, right? We're defining a method. All right, the method is called DoStuff. It accepts, so these are the parameters in this parentheses right here. That's what the program will take in. So I'm sorry, that's what the method will accept. So you send it a object of type shape, right? In this case, then internally we refer to that object that you sent as s. So s is the variable name, shape is the type of the thing you're sending into the method. All right. So then the DoStuff method, we have this shape we're calling s, right? This s is a variable of type shape. We call the .erase method and the .draw method. Okay. All right, so we're using the base type here, right? The base type of shape. Now we know that we would never actually create an object of type shape. Why would you? There's no such thing, right? It's abstract. It doesn't really exist, right? So we've created this, our base class is really for us, serves as a way for us to organize the derived classes that we're actually going to use. Okay, so we create this category, and then we're going to use it to create the derived shapes. Okay, and the real world has exactly this. Okay, you never see vehicle driving down the road, right? Because there's no such thing as vehicle. Okay, there's a car, there's a bicycle, there's a truck, but there's no such thing as vehicle, right? Everybody get that? Okay. All right. You can categorize the specific thing as into the category of vehicle, right? But there's no such thing as vehicle. That doesn't exist in the actual real world, right? Okay, so the same thing here. So we're using this base type of shape as a way to write kind of general code that will accept any shape, any derived class, right? And we can do that because their interfaces are the same. And that's this idea of polymorphism, okay? That basically you can take a member of that group, like a circle, and you can send it where the program is expecting it's the group that it fits into, like shape, right? And that the program will do something to that variable so that it can run as a shape object, right? A shape type. Okay. So the best way to think about this is that if we say are sending it a circle, circle is shape. It is a circle, but it also is a shape, and therefore any method that accepts shape will accept circle. Okay, that's basically how you think about it. A circle is a circle, but a circle is also a shape, and therefore you can send the derived class of circle to anything that will accept the base class of shape. And it works for any base, that relationship works for any base class and derived class in Java. Okay? This method speaks to any shape, so it is independent of the specific type of object that it's drawing and erasing. If some other part of the program uses the DoStuff method. Okay, so now we have our method up here. We've written this inside, somewhere, right? Okay. We've written this somewhere in our program. And now we're going to actually use this DoStuff method. So here we go. So we create a circle C equals new circle, right? So we're defining a variable C of type circle. We're initializing that variable by going new circle. So we're creating a circle object, and we're assigning C as that new circle object. Okay. We take T, we define this variable T, right, as a triangle, and then we create a new triangle object and we assign it to the variable T. Okay. We create L as a line object, as a type of the type of the L variable is line. We create a new line and assign it to variable L. So now what we have is a circle object called C, a triangle object called T, and a line object called L. Okay. Now what we can do, so the thing that is the disconnect here and where polymorphism is used is normally I have to send, not normally, but in most cases, I have to send, if a method says it only accepts shape objects, objects of shape type, I can only send it objects of shape type. That's the exception that polymorphism is, right? So if this said string S and I send it a double, it would cause an error. It wouldn't work. All right. If this said double and I send it an integer, it also wouldn't work. Okay. So normally, if we have a method that we say, okay, it accepts variables of this type, we can't send it a variable of any other type. It will cause an error. But in the case of derived classes, we can. Okay, so that's the polymorphism is an exception to this rule of programming, right? Okay, so we can send it, because circle is also a shape, we can send DoStuff the variable C. It feeds in here, right? The method accepts it, right, as a shape. Okay, it changes it into a shape type and then does something to it. All right? Okay, so everybody understands that. The polymorphism basically causes an exception in the programming language where I can use derived types as if they are the base type. Okay? Otherwise, it would cause an error. If I tried to do that with other types, it would cause an error. All right? Okay, so we can send any variable of a type that is a derived type of shape to a method that accepts the base type shape as its parameter. Everybody got that? Okay, so I'd like you guys to go ahead and write down this code. Okay, so go ahead and actually write this code out. And I'm going to make a couple of notes on here that you should also write. So go ahead and write from void down to the curly brace, and then write circle C equals new circle, triangle T equals new triangle, line L equals new line, DoStuff C, T, and L. Okay. Okay, so guys, just write out this comment as well. Okay, so DoStuff will accept variables with type other than shape if that variable is of a type derived from shape. It will treat the variable of the derived type as if it is the base type. This is polymorphism. Okay, so as you're writing, I'm just going to talk a little bit about why this is a good idea. Okay. All right, so imagine a case where you didn't use this technique. Okay, it's just a trick. It's just they added this feature into the programming language to solve a particular problem, which is the case every time there's a new version of a programming language or a new programming language. Essentially, there's a reason why they created it, and that reason is to solve some problem that they had with a previous version of the programming language, all right, or an older programming language. So in this case, it's a lot easier to write this DoStuff method one time. Okay, it only has 2 lines, right? Imagine a different case where you had to write code that was like, if it's a circle, do this. If it's a square, do this. If it's a polygon, do this. If it's a rectangle, do this. If it's an octagon, do this. If it's a pentagon, do this. Okay? That would make this one method unwieldy, right? And every time you wanted to add something, you would have to come back in and rewrite this method, or change it, or try to make it more efficient. It would become spaghetti, all right? So the idea is here that when I add a new type, I add a new shape, I only have to deal with the shape that I'm writing. I just write that one class, and I know that my other code is going to just handle it, right? So I don't have to come back in here and mess with this DoStuff method if I want to add a new type of shape. I just have to write the class for the new type that I want to include, right? So that's why it's easily extensible, right? And when they say encapsulate, that's what they mean. Okay, so when we said the word encapsulate before, it means that I can just make my new code, and I know that those changes I'm making are just where I'm writing it. I know that it's not going to affect other parts of the program negatively. Okay, that's the idea. So encapsulating those changes means that everything else is protected. Only the new code that I'm writing can have any bad effects. All right. Okay, so everybody has that note written down? Okay. DoStuff will accept variables with type other than shape if that variable is of a type derived from shape. It will treat the variable of the derived type as if it is the base type. This is polymorphism. Okay. See, big word, simple idea, right? You can write code that will accept lots of different types as long as you define that method that you're writing as accepting the base type, and then you're careful, or you follow code, you have some coding standards when you create your derived types. Okay, so if you have these simple rules as you're writing your code just automatically becomes easy to maintain and easy to write. Okay. Interestingly enough, the difficult part is the thinking, right? The difficult part is the design of the code initially, right? It's designing the objects so that later on you can use this polymorphism, right? Okay, so that's the difficult part. The difficult part is the conceptual part, not the writing a gajillion lines of code. It's kind of a trade-off, right? It's like either I can write a gajillion lines of code and not have good design, or I can have good design and all of a sudden I write very little code. Okay, that's the trade-off. All right. Okay, so that's polymorphism. I'll be honest with you, this is the type of stuff that drives you nuts when you switch between programming languages. Like Java does it this way, and then you're going to go to another language and it's going to do something different. So, interestingly enough, it's kind of most modern languages are going to be able to do this. Okay. So most ones that you deal with will be able to. I would have to look it up though, to be honest with you. Okay. At the very least, you should be able to recognize this in code. Say you want to build something on your own, you go get somebody else's code, and you're like, wow, what is this doing? Like, why am I passing an object of this type into this other method? This method only accepts this other type. I mean, obviously, then you should be like, oh, okay, so this must be a derived class. Then you can go look at the definitions for the objects, and just knowing that this concept is out there can help you to understand other code that you might see. Okay. Alrighty. Okay, the calls to do stuff automatically work correctly, regardless of the exact type of object. This is a rather amazing trick. Consider the line do stuff C. What's happening here is that a circle is being passed into a method that's expecting a shape. Since a circle is a shape, it can be treated as one by do stuff. Okay, so remember, a derived class is the type it is, but it also is the base class, right? It's two things. It is the type that it is. It is also the base class type. Okay, that's why it works. Right? Since a circle is a shape, it can be treated as one by do stuff. That is, any message that do stuff can send to a shape, a circle can accept. So it is a completely safe and logical thing to do. We call the process of treating a derived type as though it is a base type upcasting. The name cast is used in the sense of casting into a mold, and the up comes from the way the inheritance diagram is typically arranged, with the base type at the top and derived classes spanning out downward. Thus, casting a base type is moving up the inheritance diagram, or upcasting. Okay guys, go ahead and write this definition. To cast a variable what's the word I'm looking for? Means to change its type from an original type to a different type, such as integer to double. Okay. To cast a variable means to change its type. For example, from integer to double. You could also write, or from string to integer. That's casting. So to cast a variable, and it's this thing, and it comes from the need to do it comes from this is a lot of what you do in programming, to be honest with you. A lot of the errors that you're going to get are a result from casting. So for example, let's say when you guys use the scanner object, right, and you guys have somebody typing something in, you know how sometimes we use next, but sometimes we use next double, right? Okay, well if you say next, it accepts the input as a string, right? Anything they type in just comes in as a string, but that's not a number, right? So the program doesn't treat that as a number yet. Okay, then you have to cast that you have to catch the input. You have to make sure that it's going to be a number, right? That they didn't spell out the word 20 or spell out the word 10, okay? If you wanted to cast it as an integer, you'd have to be sure that it didn't have any decimal places, right? Okay, or you'd have to use something to change it into a number that you were sure could handle decimal places. Okay, so this thing of casting, where you're changing the variable types, actually ends up taking up a lot of time in programming. So it's one of those things that you just have to understand, right? So if you want to feed a method a variable, you have to make sure that that method is, or that variable is the correct type to feed to the method. Okay. So if your method is vegetarian, you can't feed it a piece of steak, right? You have to feed it an apple, right? So you got to turn that steak into an apple. That made no sense. Yeah, you just have to watch out. If you get a type error, which is it'll happen a lot. Okay, you have to want to go back and make sure that you're sending the right type to the method. All right. Okay. And usually it'll give you in Eclipse it'll give you a good error message. It'll say like was expecting string but sent double, something like that, and you'll be able to go back and cast the variable correctly. Okay, so upcasting. So basically, when we're calling this method, we're sending it a circle. And Java is smart enough to know, hey, I was expecting shape, you sent me a circle. I'm going to turn that circle into a shape automatically and then feed it into this method. Okay, so upcasting happens automatically. You don't have to worry about it. You just have to know that you can send a derived object to a method that is expecting the base type, right? An object of a derived type to a method expecting the base type, it's fine, it will work. Okay, that's basically what you need to know. Okay. An object-oriented program contains some upcasting somewhere because that's how you decouple yourself from knowing about the exact type you're working with. Look at the code in DoStuff. S-erase and S-draw. Notice that it doesn't say, if you are a circle, do this. If you are a square, do that, etc. If you write that kind of code which checks for all possible types that a shape can be, it's messy and you need to change it every time you add a new kind of shape. Here you are saying, you are a shape. I know you can erase and draw yourself. Do it and take care of the details correctly. Okay? Okay, so that's a good way to do it. So by taking the complexity and taking the complexity out of that part of the code and putting it in the classes that define the shapes themselves, it has a lot of benefits. Okay? From maintainability, you can split up that work, right? Like, so if we had 30 people in this room, we could create 30 different types of shapes pretty quickly. Okay? If we all tried to write them in one place, it'd be like you write like 30 people writing next to nothing and one person trying to maintain this giant section of code. Okay? It'd be very difficult to do. Okay. What's impressive about the code in DoStuff is that somehow the right thing happens. Let's hope so. Alright, calling draw for a circle causes different code to be executed than when calling draw for a square or a line. But when the draw message is sent to an anonymous shape, the correct behavior occurs based on the actual type of the shape. This is amazing because, as mentioned earlier, when the Java compiler is compiling the code to do stuff, it cannot know exactly what types it is dealing with. So ordinarily, you'd expect it to end up calling the version of erase and draw for the base class shape and not for the specific circle, square, or line. And yet the right thing happens because of polymorphism. The compiler and runtime system handle the details. All you need to know right now is that it does happen, and more importantly, how to design with it. Okay, that really is the important part. Okay, interestingly enough, when you're implementing this, how it happens doesn't really affect you. The fact that it does happen in Java is the important fact for you, and then learning how to take advantage of it is the really important fact, right? So learning to design to take advantage of this polymorphism, that's what we concentrate on, right? The work to create it and how it works that work's already been done, okay? So we want to know how to use it and take advantage of the fact, right? Okay. When you send a message to an object, the object will do the right thing, even when upcasting is involved. Okay, now the author's going to go into abstract base classes and interfaces. Okay, so this abstract idea is what I was talking about with, we never see a vehicle, right? We see a car, we see a bicycle, we don't see a vehicle. The vehicle is an abstract idea, right? It's abstract, it's not concrete, right? So you want to think about the categories. So the base class is like a category, right? It's a, shape is a category. It's not an actual thing. Okay, so the base class is a category. And then we make derived classes that fit into that category, correct? Okay, so think about the categories as being abstract. It's an idea we use to organize the derived classes. Okay, so there's this keyword abstract. So we want to stop people from creating objects of the type shape because it has no use. There's no, for example, if I make a class called shape, and all I do is to what's called stub out the methods, right? So if I write the methods like draw, well, the draw method in shape is not going to have anything in it, right? It's just going to be there just as a placeholder so that when I get to do circle, it's going to, then circle's going to have a place for the draw method, okay? But we don't want anybody actually creating a shape, we don't want anybody actually creating an object with type shape. So how we protect that code is we use this keyword abstract, okay? So when you say, hey, this class is abstract, that you're basically saying nobody can actually create an object with this type, right? Because it might not have anything in it. It might just cause errors, right? Okay. So often in design, you want a base class to present only an interface for its derived classes. So that's what we're saying. You might create a bunch of empty methods in a class called shape, just so they are there when you start making the actual shapes, like the circle, the square, the rectangle, right? That is, you don't want anyone to actually create an object of the base class, only to upcast to it so that its interface can be used. This is accomplished by making the class abstract, by using the abstract keyword. If anyone tries to make an object of an abstract class, the compiler prevents it. This is a tool for enforcing a particular design. Okay, so because you're using this abstract keyword, it's basically, this is a situation where it's not just you coding, right? There's one person coding, like, for example, there's one person creating these classes, these types, and another person who's like actually using the classes in code, okay? So a way that you would communicate to them, hey, don't create an object of type shape, is you make that class abstract, okay? That's basically it. You're saying, hey, this is an organizer, don't use it in reality, right? You can also use the abstract keyword to describe a method that hasn't been implemented yet, as a stub indicating, here is an interface method for all types inherited from this class, but at this point I don't have any implementation for it, okay? An abstract method may be created only inside an abstract class. When the class is inherited, that method must be implemented, or the inheriting class becomes abstract as well. Creating an abstract method allows you to put a method in an interface without being forced to provide a possibly meaningless body of code for that method. Okay, so that's exactly the case that I just described, right? If I'm creating this shape class, it's the base class, I put in like draw, but there wouldn't be any code in it, right? Like void draw, there wouldn't be any code in the method because there's no way to draw a shape, right? But then when I create the derived class, I'd put, class circle, then I would put the method draw, and I'd actually have code in it, right? I would change it so that there's actually code in it. Okay. For abstract, okay, so guys, let's go ahead and write the abstract keyword so the abstract keyword is used for a base class The abstract keyword is used for a base class when you want the base class to only present an interface for derived classes. But you don't want anyone to actually create an object of the base class. Okay, I'm going to say that again. The abstract keyword is used. The abstract keyword is used on a base class when you want the base class to only present an interface for its derived classes, but you don't want anyone to actually create an object of the base class. Okay, we're going to skip the interface keyword for a second. Okay, so basically we protect somebody that's trying to use the classes we're writing by using that abstract keyword. Okay, we don't want them to think that they can use something, but they really can't, and then they write code against it and it causes them a bunch of problems. So we use that abstract keyword so that they don't use it in an improper way. Okay, so it's a way for us to say, hey, this is just for organization. It's a way for you to write code using polymorphism, but don't actually be creating shape objects, right? Objects of type shape. Okay, this next section goes into object creation, use, and lifetimes. And it goes into what's called like garbage collection and stuff. So basically what you need to know from this section is that to make programming languages more flexible, they make you define less stuff at the beginning. Okay, so for example, C++ is very, very, very fast, but it's fast because it makes the programmer follow very rigid rules as you are programming. Okay, and one of these rules, and it executes code in a different way. Okay, so I'm going to go ahead and read this, but you guys don't need to write anything down. Okay. Technically, OOP is just about abstract data typing, inheritance, and polymorphism, but other issues can be at least as important. This section will cover these issues. One of the most important facts of objects is the way they are created and destroyed. Where is the data for an object, and how is the lifetime of the object controlled? There are different philosophies at work here. C++ takes the approach that control of efficiency is the most important issue, so it gives the programmer a choice. For maximum runtime speed, the storage and lifetime can be determined while the program is written by placing objects on the stack. These are sometimes called automatic and scoped variables, or in static area storage. This places a priority on speed for storage allocation and release, and control of these can be very valuable in some situations. However, you sacrifice flexibility because you know the exact quantity, lifetime, and type of objects while you are writing the program. If you're trying to solve a more general problem, such as computer-aided design, warehouse management, or aircraft control, this is too restrictive. The second approach is to create objects dynamically in a pool of memory called the heap. In this approach, you don't know until runtime how many objects you need, what their lifetime is, or what their exact type is. Those are determined on the spur of the moment while the program is running. If you need a new object, you simply make it on the heap at the point you need it. Because the storage is managed dynamically at runtime, the amount of time required to allocate storage on the heap can be noticeably longer than the time to create storage on the stack. Creating storage on the stack is often a single assembly instruction to move the stack pointer down and another to move it back up. The time to create heap storage depends on the design of the storage mechanism. The dynamic approach makes the general logical assumption that objects tend to be complicated, so the extra overhead of finding storage and releasing storage will not have an important impact on the creation of an object. In addition, the greater flexibility is essential to solve general programming problems. Okay, so what I'd like you to come away with from that paragraph for now is basically that Java and other programming languages are slower than C++ and some other programming languages because of the way they handle data and memory on the computer. And when I say memory, I mean the physical memory of the computer. Okay, how they write that and how they call it and how they manage that memory. All right, and essentially what you're doing, it's a trade-off. The more flexible it is, the slower it is. The less flexible it is, the faster it is, right? Okay, so there's this trade-off there between flexibility and speed. Okay? Okay, now that doesn't mean that it'll be that way forever. It's just the programming languages that are out there now, that tends to be the trade-off. Okay? Okay, Java uses the second approach exclusively. Every time you create an object, you use the new keyword to build a dynamic instance of that object. There is another issue, however, and that's the lifetime of an object. With languages that allow objects to be created on the stack, the compiler determines how long the object will last and can automatically destroy it. However, if you create it on the heap, the compiler has no knowledge of its lifetime. In a language like C++, you must determine programmatically when to destroy the object, which can lead to memory leaks if you don't do it correctly. Java provides a feature called a garbage collector that automatically discovers when an object is no longer in use and destroys it. A garbage collector is much more convenient because it reduces the number of issues that you must track in the code you must write. More important, the garbage collector provides a much higher level of insurance against the insidious problem of memory leaks. Most programming languages, not most, many programming languages provide this garbage collection feature. Right? You should assume that the programming language you are using has a garbage collector unless you're told differently. Okay, by the time you're programming these languages that don't like C++, you would understand that. Okay? All right. Okay, so now we're going to talk about collections and iterators. Okay? Okay. Okay, so you guys go ahead and write a collection is a container which holds other data types. A collection is a container which holds other data types. These include list classes, map classes, set classes, and others. Okay, so containers, I want you to imagine a container object in general as either a list of things, like it's just basically like you're taking, I want you to think of it like a spreadsheet, okay? Everybody knows what a spreadsheet is, right? Imagine that instead of a number in every box, that the spreadsheet is like, not imaginary, but you can't see it, right? But you can hold an object or any other variable in any box, okay? So it's just like a spreadsheet, except you can just use one row, right, which would be kind of like a list. You could put object A, object B, object C, object D in each of those boxes, okay? So you can hold them in each of those little boxes on a spreadsheet, right? You can have two-dimensional arrays, right, or whatever they're going to call them, right? But you can have two-dimensional, what are essentially spreadsheets, right, where for every row there are multiple columns, right? You can have three-dimensional arrays, right? So you can have for every row, I don't even know what you call that. So for every row there are multiple columns. For every column there are multiple stacks backwards or forwards, however you want to view it, right? Okay. So you can think of it as almost like a cube, right, of a spreadsheet that's actually a cube, all right? So, but at the end of the day, these collections are just ways to organize data so that you can efficiently loop through them, okay? And that's where the iterator comes in, okay? So, it's a way that a collection is a way to organize data so that you can efficiently process it, all right? Whatever that might be for your current situation, okay? And we'll get into this later. Okay, so you guys are going to get into arrays, and in general, people tend to kind of fall onto, people tend to do the same type of programming a lot, and what happens is they tend to start using the same these collection types in general. Okay, the most common one that you're going to see in Java is this array list. Okay, and that's essentially a lot like a spreadsheet. Okay, an array list is a lot like a spreadsheet. Okay, so the last thing that we're going to write, an iterator is an object whose job it is to select elements within a container and to present them to the user of the iterator. Sorry. An iterator. Sorry, let's say it a different way. The job of an iterator is to select elements within a container and present them to the user of the iterator. This seems complicated. It is not. It's a loop, right? That's all it is. Okay, so basically imagine you have a spreadsheet. Okay, that's the container, right? An iterator would go, oh, okay. The iterator would basically go, oh, I'm an iterator. Okay, here's the object in row 1, here's the object in row 2, here's the object in row 3, here's the object in row 4, here's the object in row 5, here's the object in row 6. Right? So the iterator just kind of loops through and lets you kind of deal with one piece of information at a time. That's what an iterator does. Okay? And we basically we know these as like do while loops, while loops. You guys are very familiar with JavaScript, right? So you guys, when you process those images, you used an iterator. Okay? So basically what you did was you read every pixel into a container or a collection. Okay? You guys remember that? Okay, so you had this image, right? You read every pixel of that image into a collection. Okay, you called it an array, right? Okay, I think. Did you guys call it an array? I'm not sure if you did or not. Anyway, so you read each pixel into a collection, and then you used an iterator, which you called, it was do while, right? So, or it was do, what was it? It was for. It was for pixel in image, right? Okay, so that for loop is the iterator. Okay, that's what it is. A for loop is an iterator. All right, guys? So you're very familiar with them already. So once again, complicated word, simple idea. Okay? All right, guys. We are officially finished with 4 of 6. Okay. You guys have been very patient. I appreciate it.